Okay, so where to start? I, being me, think about a lot of things, and I kind of have like a mental index of different things I go through in my mind before I decide to go out on public street and start talking about things. So when I say I've tested something, usually what's gone on is there's been a day and a half or 2 days worth of me dicking around with something, or sometimes months or years, like the LTO batteries. I took a lot of time looking at those before I come out here on the YouTube Gargler and I talk about it. So today we're going to once again revisit the RSP, or not RSP, the DPS-1200sb's. We're going to keep holding this up in front of the camera for a minute. So what happened yesterday, actually the day before yesterday, and this has happened ever since I come out with these switch modules, is people say they used Ohm law to defend themselves, which is cute. Ohm's law is a real thing, and we don't ever get to break it. At least we haven't figured out a way to break it yet. I feel like the math is wrong, but that's a conversation for another day. Look, this unit here, this is supposedly, underneath most ideal conditions, okay? On 110 volts, or 120 volts, it's a 900 watt power supply, okay? It pulls about 9.5 amps to run this unit. That's on this side of things. And it puts out 900 watts at 12 volts. It cannot hold 12 volts, by the way, y'all. That's my biggest problem with everybody's argument. They read this data sheet and they think that they're a rocket scientist, and they're not. They just know a little bit about a bigger picture, right? I had a gentleman yesterday or the day before yesterday, and I'm not going to put his comment in the video because I don't want to make fun of him. That's not what we do here. But what it did do is it motivated me to think, hey, let's do a video, right? And his comment is I wish technicians would quit lying to people about the output ability of these power supplies. And my eyebrow went up. This is a guy that took 10 of them and put them inside of a cabinet right out the hop, and then took that to like 1800 amps. And it held the voltage. Just keep that in mind. So, look. The only time that we get to actually use the 1200 watt rating on these supplies is when there's 220 volts coming into them. So that's what we have. We have this hooked up to 100 amp, 220 volt outlet. This is not going to start for power. Impossible on this side of the street. So we can just go ahead and just dismiss all of the arcane variables that would come along with this thing not having enough juice to feed it to do its job. Okay? This is a completely unaltered power supply. I haven't done anything to it yet. The output on this thing at 100 volts is 800 watts. If we put 120 volts on it, it's 900 watts. And if we put 240 volts on it, it's 1200 watts max output. I'm not debating that. You'll never get me to debate this on the sticker. And that's set up the way that they constructed the supply. This is a device that is built for a standard. That's my problem that I have, is that everybody, Ohm's law, blah, 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 blah. Got it. No one's saying you're wrong. The problem is that we go in and we alter the supplies, and as soon as we do that, most of this data is out the window. If we change the voltage, that means we're going to lose amperage. There's no way about it, okay? As soon as we go and we ramp the voltage up, we're going to have a slight decrease in the output amps, okay? So if we go to 15 volts, these really drop down to what I would consider to be 85 amps continuous duty. The sad thing is that the people in the comments section don't ever think what they're actually putting in the comment section and stating as fact when it's not, it's just their opinion. We, you, me, everybody else, we don't use them as a continuous duty supply. We use them as an intermediate 30% duty cycle peak power device. If we do the math and we sit down and we think about it, the amount of time that the unit is on versus the amount of time the unit's underneath a load, it sits at maybe, let's say 100 amps is output total on this thing. We'll maybe put 25 or 30 amps worth of base load against the supply, and then we pulse the supply up to an envelope of about 100 amps per supply. And then it only stays in operation for 30% of the time that it's on. These are 100% duty cycle ratings that are on this tag. So the fact that we're not using it 100% duty cycle allows us a little bit of fudge room with what we can do with the components internally. Think about it. Now, what set me off is this guy literally put himself out there like he was a defined expert, ordained by God himself, ornated with, blink on the head. You guys don't know what you're talking about. I wish technicians would quit lying to everybody. We're not lying. We're telling you the truth. This unit right here, I'm going to show this to you on video, can produce, honest to engine with a 220 volt feeding it, about 75 amps before this drops below 12 volts. Continuous. When we load it at 80 to 100 amps, which this thing is rated to hold 12 volts at 100 amps, it actually works out to be about 11.8, 11.7 volts is what the supply runs at. Now the output crowbar protection, which is the ability to keep itself from being shorted out, is such that we can't use them in anything that we have because it's too sensitive. So we have to take that sensitivity away. We have to dumb it down. We have to tell it, hey, relax. There's going to be some energy pulses. You'll be fine. Don't put yourself in crowbar protection. So the only thing I've done with this thing so far is I've added an on-off switch. Now here's another little piece of information that if you're only armed with the little bit of information that's on this data tag, you out there in the gargler land, you can set yourself up to look like an idiot. Here's my argument that I have against all of this. It says max on the data tag. This is an HP 1500 watt switcher. 300 more watts of output power than this unit. Okay? This puts out 1500 watts at 12 volts, so technically this is 150 amp supply. The only major difference between these two units is the fan. The fan butties. There's a compound fan that's in this unit. It fits in the same server location. It's got the same blade on the output. It generally has the same rectifiers on the inside. It has generally the same MOSFETs on the inside that do the switching. It has the exact same filtering caps on the internal side of it. It has a little bit different control board because it's built for a different spec. But the majority of the parts that are inside that make this work are, guess what, the same. There's probably a 25% difference between this top unit and the bottom unit, but the main core components, the filter capacitor, the transformers, that kind of stuff is the same. The big major difference as far as the footprint is concerned is the compounding fan. So I went back to Homeboy on YouTube or on Facebook and said, hey man, just trying to give you more information. So I'm trying to keep you from looking like an idiot because this guy has paraded himself around Facebook in many different groups and talked like he knows anything about what he's talking about. This is actually internally 150 amp supply with a smaller fan. And the reason they can get away with derating it and putting a smaller fan on it, well, they can derate it anytime they want, put a smaller fan on it, is because you're not going to cause internal components to get as hot. It makes logical sense. It really, really, really does. Really does. Period. Okay? I'm not saying that we can go and make this into a 150 amp supply. That's not our goal. I'm saying that the only major difference between this unit and this unit, primarily from the outside, is the fan and the control board. There's more headroom in the power supply than you would think. There's a lot more. I mean, a lot more. That, and we're using it in an intermediate duty cycle, not a continuous duty cycle. So then he came back and says, well, once you go away from those UL ratings, it's now dangerous. The instant we open the case on one of these, the UL rating goes right out the window. So that argument means 0. The UL ratings in our situation, the way we use it, is a suggestion. It's just an honest suggestion. Because what we're doing with it, we're modifying it. So you can't glom onto this data. Now, the parts of data that you can take that are going to be very valuable to you, the builder, is the input voltage, okay, number one, and the current draw that it's going to use to achieve X output. Right? So if we know we got it on a 110 volt lead, it's going to pull 9 some amps, right? That, and so then how it works, that's about a 75 amp power supply, 70 amp power supply when it's 110 volts. It ain't no 100 amp supply. Remember, because when we go up in voltage, we lose amperage. You have to give to get, right? So you got to go down on the girl to get her to go down on you. It's just part of life, right? There's a sacrifice, there's a trade-off. So if we go down in voltage, we can increase our amperage output and goes way up. That's just the universal law, man. That's just how this works, okay? Bottom line. Bottom line. Hence the reason why you can take a microwave transformer and take the secondary out of it, put 2 turns of wire through it and have 1,000 amps or 5,000 amps out of a microwave transformer, but it's like at 1/10 of a volt. It flip-flops. I mean, 1,000 amps I think is a little bit absurd, but I did see a protonification where he took a microwave transformer and put like 4-aught gauge or 500 MCM wire somehow, and he managed to get 2 turns through the transformer, and he was getting like 1,200 amps out of a microwave transformer. Of course, he was overclocking it with 220 and blah, 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 blah. But the point is that you have to give to get. So if you're going to go up in voltage, you got to give on the amperage. And so what that means is, on our side of the street, the way we use the thing, we have to add another supply. Okay, so this supply now, instead of being 100 amps, is really ultimately like 80 amps continuous. So the question is, how far can we surge this before the thing blows up? That's what we're going to do today. First, we're going to test it the way it comes out of the box, and we're going to get ourselves a baseline. It's called data points. If you want to come talk to me about this, don't quote to me the stuff out here on this data sheet. Don't. I won't listen to you. Now, if you tell me, hey, BBI, I got one of these modules. I plugged it in. I started doing modifications to it. I load tested it. Here's my data. Here's a video of me sharing my data so you can go watch it. Or I wrote it down and took notes. Or I took pictures. Or I took a video on my phone. I got on my Polaroid camera and I took old school porn pictures of my girlfriend. And then, oh, by the way, in the background, I was doing this. I will look at that kind of stuff. That, and I want to see the boobs. Because I'm a dude. I like boobs. We all want to see every boob ever made. We're all guys. We hanging ones, swinging ones, slapping together ones, flapjack ones, trucker booby. We want to see them all. At the end of the day, I want to see all the data. Give me where you've gone and experimented to me. Don't get yourself up on Mount Carmel like you're coming down off the hill with 10 commandments and talk to me about what's on this data tag. Because the instant we open this lid and we start adding resistors to it, all the data here goes out the window. So we need to stop this. This needs to stop happening. We cannot go, oh, 10 modules, 1,000 amp supply. That's really about an 800 amp supply in a continuous duty output format. That is correct. That's 1,000% correct. Now, if we take and we put, let's say, a 200 amp load on 10 modules, we can probably pulse that over to about 12 to 1,400 amps. Do we want to do it all day long every day? No. Is that the way we're designing the power supply to operate? No. Is that the way we operate the equipment anyhow? No. There's other variables in the equation that you have to take into account. And I love it when people quote to me Ohm's Law like I've never read the book and I have no idea how Ohm's Law works. And everybody always leaves out one little key factor of Ohm's Law. It's not volt amps. It's not volt watts amps. They always leave out the last little bit, the efficiency. What's the efficiency of the device and what's the efficiency of the circuit consuming the current? The efficiency is the other half of Ohm's Law. So I won't hear it. Stop. If you're going to come at me, come up with the real data. Because then I'll go out, and if you come at me, I'm going to come out and I'm going to do another video like this and be like, ah, see, sorry, you're wrong. You're just wrong. You're wrong. Now, in today's world, it's really hard to have a rational adult conversation. Let's see here, 0. Rational adult conversation without somebody having their little emotional feelers get smacked into the ground. We're going to go ahead, we're going to turn this on. The fans in the carbon pile are going to consume about an amp worth of shmoo. Unadulterated, unmolested, untouched power supply puts out 12.29 volts. We're going to have 1 amp worth of idle current against it. Let's start bringing on the load. Here we go. There's 70, 90, so around 100 amps worth of draw, 110 amps worth of draw. Look at where our voltage is resting, 11.84. Now, because we have not altered anything, we don't have a 100 amp supply. Let me back this down. We'll stay 90 amps. So now we're technically running it under its rated power because remember, nothing is 100% efficient. So we'll back it down to about 80. And around 80, we get almost to our, there we go. So if we sat down and did the math, we'd probably see that we're consuming about 1,200 watts worth of shmoo at about 76.7 amps. We're consuming about 1,200 watts worth of shmoo out of the supply. And the rest of it we're giving up to the gods in loss, in inefficiency, either it being heat or lack of contact point here on the supply, the wire, because remember, I'm not probing it here, I'm probing it over here. Even though the amperage is consistent in the circuit, it's universally the same throughout the circuit, you're going to have loss points that's going to cause you to lose volts. That's why I'm probing here and not over here at the supply. So it's just sitting here idling away with 30 amps on it. Now this is not going to get our attention doing this, right? The supply is designed to have 1,200 watts worth of load on it and for it to safely run now till Jesus shows up. 11.98, 0.2 of a volt. Well, how do we know we're not losing 0.2 of a volt in the wire? Just keeping it real, we're keeping it on the level, right? Remember, that's with as much current going in as it possibly can drink. And we'll sit here all day. The carbon pile will give up before this power supply starts to give us a problem. Eventually the fan will ramp up when the power supply gets hot enough. The internal thyristor on the inside of this thing is going to go, hey, wait a minute, I got too high of ambient air, help me out, and it'll start moving more air through the supply, cooling off the heat sinks, cooling off the diodes, cooling off the filter caps. We can sit here and we can do this all day long. We have already sat here and talked longer than most people would have their amplifier keyed down or their radio piece of equipment in full load operation. Power supply does not care. That's because this data tag says that they have designed this thing to do exactly the way we're using it. At this voltage, with this feed current, with this load, this is what this supply will do. We'll sit here all day. This supply will catch on fire and fail before that thing quits. Food for thought, right? Okay, so now if we start crawling over, so we'll put 100 amps on it. There's 100, 110, 120. we're already 25% over its rated load, and we've only lost about, what, 1/4 of a volt? And it's still holding on like there's no big deal. So we'll go on up. Now look at where that volts start to drop. You see that? So let's back the load off. And the wall in the sand, because the power supply is trying to protect itself, the wall in the sand is about 6 amps. 127. Look at that. So we know that we can overclock these by 100 and, or we can overclock these by what? 50 amps out of the supply? And still stay within less than 1% of the total output rating of the supply. Let's keep that in mind. I want everybody to think about that for a hot minute. So at 80 amps, it maintains 12 volts. So for us to pull it down, for us to pull the current down any further, or to pull the voltage down any further, pardon me, we have to overclock it from 80 to 127 amps. That's 47 amps difference. So we can overclock the supply by 50%. We still haven't had failure yet. Nor do I think we ever will. This supply will eventually just shut off. The carbon pile's really starting to stink. So now look at the supply voltage. The load hasn't changed, but look at the voltage. So we'll back this off. Now we're at 116 amps. And we're floating at 11.8. We can do this all day. Let's let the pile take a break. I'm going to let the power supply cool itself down. And we're going to start to modify this. We've demonstrated that this device is designed to sit in a server rack and produce 80 to 100 amps worth of shit with 220 volts feeding it, and it's all within spec. Like I said, unmodified. We are going to take this till I have flames blow out of the top of this thing, or something inside this hard quits. We're going to find out. So our first step that we're going to do when we come back is I'm going to put in a 12K resistor and I'm going to trim the voltage out for 15 volts. I suggested in this post yesterday on Facebook that I like to set these at about 15 too. The reason for that is after we go through the loss of the wire, the loss of the connections at the supply, going over to feeding whatever we're going to go feed it to, all the different little hoops that the electrons have to jump through to get to the component. If we were to measure at the component side of things, that would be i.e. the transistor. If I'm feeding 15.2 from the supply, the transistor is probably seen around 14.8 underneath full load, because there's a little bit of voltage loss that's in the circuit. Remember, once again, the amperage stays the same. The voltage is what is the motivating force here, right? Ohm's law. And the efficiency of the circuit to which the device is in, period. We're going to modify this with a 9K crowbar. Right now, it's like 100 and some K or 10, whatever it is in there. Let's go ahead and see where this thing actually trips out and goes into crowbar. Giving it a chance to cool off. It's still relatively hot. The pile's relatively hot, but here, let's go ahead and we'll take this up to failure so we can get a data point. And it should drop out at about 10 point something volts. 130, I'd say 129 is about the max we get out of this. Yep. So we just took it to failure. Voltage shuts off, the fan stays running. The fan in the supply stays running. So the crowbar protection has just kicked in and said, I've got no more I can give you. It's time for us to be done. So now we'll shut the supply off with our switch, and we'll cycle it back on, and we come right back to life. That's the beauty of crowbar protection. I don't think that we should ever eliminate that. That's why I say let's decrease its sensitivity. That way we can sit here and pulse it. I've covered this in many a YouTube video. We can sit here and pulse it and it doesn't trip out. Remember, 130 amps is the hard line in the sand. We're not going to get any more voltage out of the unit. We're not getting any more amperage. It's 129.7 amps. Are we going to see that line in the sand change? I don't know. Let's go find out. You, me, and everybody else is going to watch this. Let's go learn together. Our little supply has never done anything to nobody, and we're just going to destroy it over a Facebook comment. So, looking at 151 degrees after that whole monologue that I just put down. So we'll take that as a baseline. They're designed to sit there and operate around 150 degrees, which makes sense when you convert it to Celsius, because of siliconite migration and transistor failure and that kind of stuff, and the insulation material on the rectifiers and stuff. There's about 80 Celsius is the line in the sand, right? We go above that, we start having problems. We stay below that, we're relatively safe. So if we engineer our way into a corner, which that's what HP has done, you know that if you create a product that puts out X, you can certify it for Y, okay? So 150 something degrees. This thing is warm. Well, we're going to do our crowbar protection. We're going to modify that, and we'll do a little bit of voltage mod, so we can test it in our real world, how all of us like to use it situation, and we'll see where we're actually at. I think that we're probably going to be in the 70 to 80 amp range, once again maintaining our baseline voltage reference, I think, pretty sure, and that's underneath continuous load, not pulse load, two different things. And we're just desensitizing the crowbar. I am not an advocate of eliminating the crowbar, which we are going to eventually do to the supply. We're going to take this thing and we're going to shut off the crowbar protection, and we're going to take it till this thing pops, something blows up, or smoke starts coming out. So I'm not an advocate for that, by the way. I feel that we still should let the crowbar protection do crowbar protection things, and we should utilize this to help keep our components safe, help keep our customers safe. We don't want to go too far astray from what is the suggested operation. I just feel like we can maybe knock down the sensitivity. Remember, this is designed to be used in a computer farm where we have to keep our voltages very stable and smooth and ripple free, right? So we'd rather shed the load off the supply versus having some kind of weird spike take place. So we need to back that sensitivity down. Once I put a soldering iron in here to do anything, everything on that data tag is out the window. Okay. About 10 minutes later, we're back. I had to do a freaking battery change and a bunch of stuff, but if you notice, we've dropped 1/10 of an amp by going up in volts. So we've increased the voltage on the supply to 15.2. We know that the maximum amount of voltage that the supply can put out is 16 volts because the output rail filter capacitors are 16 volts. So we can change those out, and we've me personally, have successfully overclocked this thing to around 22 volts. Okay, but that's beside the point. The one thing I will never talk about, and the one thing I strongly suggest that you never mess with, is the thermal cutout for the crowbar. You don't want to ever mess with that. And what I mean by that is if the supply gets too hot, it will go into shutdown mode to protect itself. We don't ever want to mess with that, ever. I know how to do it. I read about it. You can go find it. It's on the internet if you're really interested in messing with it. It's nothing that we want to touch, change, add to, modify, or alter. Once we start changing that, man, the thing could just run until it catches on fire. And we don't want that. We want the supply to be able to shut itself off and protect itself. Remember, the whole motivation behind this is finding a better supply than the 30 amp Chinesium, no URL or UL underlisted, no rated, no nothing, no data, no LED supplies that we were stuffing in amps for years, right? And the old timers are smart. The guys that come before me, they knew about these supplies. These things have been around forever. The problem was availability and cost, okay? And just by chance, by luck, and I've said this many a time, I just happened to find the right guy that had a surplus of these that was trying to offload them because he wanted to make room in his warehouse. And we all benefited from it. Now the guy that's out there having to drag himself up on the cross and beat himself on the chest about the label on this thing, that's what we're here to talk about today. So let's go ahead and let's start getting some data. I'm done talking about that. Let's get some data. Remember, I said in a previous segment, about 2 segments ago, that I set this up at 15.2 because underneath operation I want it to be around 14.5, 14.6. So let's go there real quick. Look at that. 83 amps, 14 volts, 14.9. So go up to 100 amps. We're going to park it around 100 amps, and we're at 14.8. So now we're going to have some line voltage loss that takes place in most of our applications on both sides, the input of the 220 volts and on the output. But we can clearly see it's easily able to hold 100 amps continuous and still stay within the safe range at 14.8 volts. That's not bad for voltage sag. That's really not bad at all. Let's back this off just a hair. We'll just keep it over a hair over 100. I want to prove a point. So I'd say a lot. We're proving a point right now. Remember, we'll use the slides this morning. We'll put it in the slow down this. I've already done this one, so I don't want this to. They don't get it because it's there. If you're 18 switches running that much noise, you really hammer on the slides. Or you got it in the situation where it's not even there. Still around right now. Let me know the record. There's only make our supply with 2 modules in it. So for me personally, as a builder, ultimately that's who's responsible. You as a builder, you're the one who's responsible for it. Maintaining it, you're the one who's responsible for the power supply. You, whoever you are, is building with modules. You personally know, if I need a 200 supply, I put 3 modules in it. I will not be in 3 modules for maximum operation. Or whatever. Because ultimately, at the end of the day, whoever the builder is, they're manufacturing whatever. But I built all the build, right? Please note the fans and the switcher have like 2 more speeds they can go to. Let's fire up the old FLIR. The switcher over here is just cooking right along. Its max temp, anywhere on that case, is 111 degrees. Just want to knock down when I will air down. Oh, you got me, cool stuff off. So this is consistently 110, 105 somewhere, 109 right now. That's top of it, 102. I'm going to draw. The blade is already a lot, it's 120 degrees. No, that's exhaust here, it's not matter. It's exhaust here. 103 degrees. Don't beat on the slides. There's no way we use it very well. Now, now it's still about 10 days. I don't know how long my battery's on my camera, how much S part does that. I know we're coming up on 10 minutes now. Get on to load. Carbon files, happy, switchers, you might be mad at this fans, I see mode, first stage. 118, 116 degrees. Remember here, it's after we're damaging parts in the slide yet. We're just at power temperature. Anyway, we have the same amount of voltage drop at 12 volts 80 amps versus 14.8 100 plus amps. Here, keep that in mind. Okay, so now everything's really hot. Yeah, see, we're still well within safety bounds here. I'd say the bunch will be saturated between 190 degrees and 100. So now we're going to put air on the unit, like, inside the any kind of supply, any level of air in the unit. It will set off, so it's just kind of, it will set off, just in air walking across it. This is on the low side, this is high side, this is low side. So just kind of air is kind of circulating by the cabinet. 120 degrees. I don't see any radical temperature rise here. I just don't. 121, 122. We've been going now for about 15 minutes. It reset it, it shut itself off. So we're going on 30 minutes worth of 100% duty cycle on the supply. Where are we at? So a half an hour in with a 100 amp load at 14.83828 volts. We're seeing maybe a couple degree rise in temperature. You know, when I first got in this hobby, I always thought that when people said something did something, there was some dude in a lab coat someplace in a very squeaky clean environment, you know, that was testing these things to failure, and he was the one that put the sticker on it. Come to find out, that's not the case at all. The best that we're going to have is somebody like me that's willing to go out and try and do this, waste their precious minutes of their life testing this stuff for your all's benefit, right? Now the fan is actually slowing down a little bit. We're still over 100 amps. We're still at 14.8. Nothing's changed. And oddly enough, the supply is getting warmer. Ever so slowly. So we'll let the thermal rise be the dictator. So we'll say that we're about 35 minutes into this test. And let's go ahead and back it down to about 80 amps, 90 amps. So look, our voltage has come up. And it's going to take a long time for the thermal to change inside the case. Because remember, there's just a silicone heat transfer that's between the outside of the case and the primary guts. Pulled 10 amps of load off the situation here. And now we should stop seeing the thermal rise. So we'll say this is a 100 amp continuous duty supply for 30 minutes. How about that? And then we'll say 90 amps. Here, we'll really give ourselves a break. Back it down around 80. Yeah, see, now it's starting to cool itself off. So it's basically a 90 to 95 amp supply continuous duty, even though that's not the way we use these. See, now it's losing temp. Slowly, 1 degree at a time. Still impressive to me. Let's ramp this back up. We'll get back up around 90 amps. Because my gut's telling me we're going to be around 90. All right, let's just let it sit here and bake. So we're almost an hour into this little test. And we're back up to 120 some amp, or 120 something degrees, 123 degrees. So we'll call it. We'll say it's a 90 amp continuous duty supply. Let's go take the load off the power supply, take the load off the pile. Let's let everything cool down. And look, the fan's going to slow right down. Just like that. Remember, this is the absolute highest temperature that's viewable in the window. This is where the crosshair temperature is at, okay? So just within seconds, I mean, literally like half a minute, we've already dropped 10 degrees out of the power supply. I say it's 90 to 95 amps continuous duty at this voltage. So, wow. Okay. So we're down around 105. Now let's go beat on it. Remember, it fell out around 10 volts. It was like 10.8 or whatever it was before. Let's go find out where this falls out with the crowbar protection now. 133 amps. So we've already got more out of it than what we got before, because we couldn't get it over 129. It's about 130 amps max. Now we're all the way down to 10 volts at 132 amps, and we're not going to get any more. All the way down at 8. That's our crowbar protection that we've altered. It's the reason we're able to pull 2 more volts down, but we're only seeing 132 amps, so we're seeing about 3 more amps out of the supply. But it really, it's after what? Let's load this back up again. So 132 amps. At 132 amps, it is a positive 12 volt supply. So at 100, let's back this down to 100. Come on, there we go. Wow, the difference between 130 and 132 is amazing in the voltage, isn't it? So we'll say 131. 131 amps. Keep it steady above 14, because at 132, it drops down to 10. Check it out. See, it just won't give us anything more. And the supply is maxed. I mean, it's pissed. $151 degrees. So that supply is screaming on the inside. Screaming. So we know that we can pulse this up to 130 amps per module and maintain above 14 volts. We've proved it on video right now. And that was after almost an hour of running it at 14.8 with a 100 amp load. I consider this safe operation. Taking into account we only load the supply to its full potential 30% of the time while it's on. Where does the crowbar kick in? I guess that's our next question. And for this, I want to put on some earmuffs, because everything inside of this thing is as hot can get. See, that ain't that bad. It's already down to 128 degrees. So where's this trip? What voltage does this thing trip out into crowbar? With 9K on the crowbar side. Okay, about 8.6 volts. And now it's in full crowbar protection. So cycle the supply off. Cycle the supply back on. Let's repeat the test with the power supply hot. Here we go, 130. So 8 volts, 8.04 volts is where it drops out on crowbar protection versus 10. So by adding that 9K resistor to things, it desensitizes it by 2 volts. This is stuff I've already done. I'm just recreating a test I ran over a year ago at this point. I don't care. This is still an impressive number to me. Oh, I jumped up too fast. This is an incredibly impressive number to me. $80, $90, $130. The fact that we can overclock the supply to 133 amps without parts flying out of it. And still maintain above 14 volts. That's an impressive number. Okay, let's shut the crowbar protection completely out. Let's bypass that completely and let's take this thing to failure. Anything for science. So now we've got the switcher hanging wide open. The crowbar protection has been removed with a shorted wire. I've never tested this. I don't know how this is going to work. I don't know if it's got an internal fuse on it or not. I feel like I'm doing a full auto frickin' let's run it till the machine gun melts down kind of video. So let's put on some safety squints. We're going to put on some hearing protection because I don't know where or how this is going to fail. Hopefully it's smoky and epic so you guys out there in YouTube land can talk about it. And when I keep referring to us, I'm not talking about the amateur community, I'm talking about the CB guys, because they're, let's face it, the CB dudes are usually the ones that take everything to 11, right? So, I mean, all love to my CB brethren, but let's embrace it, guys. We're really hard on shit, okay? Because we have one friend that said to another friend, hey, you know, he doesn't know what he's doing because, you know, my 8-pill does 4,000 bird and 16,000 watts or some shit. So somebody tries to do that and they blow their shit up instead of just recognizing it's a 2,000 watt amplifier. So, okay. Let's see if we can let the smoke out of this thing. Here we go. 130 amp load. Oh, the crowbar still kicked in. Oh, oh wow. Talk about anticlimactic. Oh, I wonder if we can squeak a little bit more out of it. Where's my tuning tool? So we'll go the other direction with it. All right, so let's try this again. All right, so I'm gonna have to adjust. That should be maxed out. .3. Oh, there's already underneath a full load. Let's reset the supply. The carbon pile got stuck. No, the best way to operate this is with it right up the middle. So, okay. Let's make it do absurd amps and just hold it there till something fails. Because eventually something will get hot enough and it'll quit. I'm still yet to figure out what we're doing to these things that's so dangerous that the guy was talking about on Facebook. It's between you and me. Because eventually we'll have failure because there's no there's no air movement on the supply. Actually got a higher output of amperage. Yeah, so it's the control MOSFETs that are getting hot. Oh, them puppies are going to blow. (340 Fahrenheit, 374, 378, 377. And it just shut itself off. And it's not coming back. All right. Maybe that was it. Maybe we just killed it. Oh, it stinks. So it is possible to kill one of these. Yeah, it's not even trying to turn on now. There it goes. So it didn't make for great video failing, but the way it failed is a very good data point. There's really no way to overload the supply to where somebody's going to get hurt, where the thing will like blow up or catch on fire. That's very interesting. Let me, I'm going to shut this off. Oh, it's back. Okay, so there's really no way to kill these things. Right back to 100 amp output. Just max it out and hold it and see what happens. Isn't that interesting how if we back the load off a little bit and let the voltage come back up, the power supply actually puts out more? So look, that's 130. That's the lowest we can pull it on the voltage. And the power supply is protecting itself. I mean, that's almost halving the voltage. Something's got to be ready to give. There, it just went again. 388 degrees. And it comes back to life. Okay. To me, this is an amazing result. Because I thought that I could just bypass the crowbar protection, hit it and hold it. Man, it's got other interlocks. It's got... Wow. Wow is all I can say. So let's see what happens. I got 129 amp load on it. We're resting at 13 volts. I mean, this is just about as abusive as you could ever possibly be to this supply. God, the inside of that transformer right there is just screaming hot. It's gotta be. I want to put safety squints back on. Nope. It just shuts itself off. I'll be damned, this thing is almost indestructible. Well, a result is a result. Any way you take it, it's got to be a result. Good, bad, or indifferent, that's our result. When it cools down, it'll come back. Well, there we go. Let's try one more adjustment. Let's see if we can get it to fail. So that's 129.7 amps worth of draw. We're pulling it down to 10 volts. No airflow. I mean, how negligent do we got to be on this before we have failure, right? I mean, this still is really abusive to the supply and we haven't had it fail yet. Oh, we're up to 166. Okay, I want to back away from it now. See what happens. Already got it hotter than it's ever been before. God, I can't believe it's not blown up yet. Yep, just shut off. So we got it up to 462 degrees. That's by us changing the thermal cutout limit. Look, you guys, I have always attempted to do my due diligence for anything that I've ever recommended for any of us to use. Because I know people take what I have to say very seriously. So, you know, I've never tried to short it out with the crowbar protection completely bypassed. So now we have our thermal interrupt that's protecting us and keeping the unit from catching on fire and blowing up. In theory, everything in here should blow up at 460 degrees Fahrenheit. I mean, the solder that's holding the components together has got to be liquid at this point, right? Think about it. we're not going to get a more heavy result. We're not going to get any parts any hotter than this. See, I thought for sure that this bridge that's right here on the corner was going to launch its guts completely out. Or the MOSFET drivers are going to blow their guts completely out. And we're already down to 320 degrees Fahrenheit on the drivers. Well, gentlemen, I'm going to take this as a result. To the keyboard warriors on Facebook, I'm sorry, you guys. The worst that happens is the power supply goes into protect mode. It saves the parts. There are no smoke. There is no flame. It pulls back and lets itself cool off, and then it comes back. Okay, so let's wrap this up here. It's the next day. The module is completely cooled off, and now it doesn't power up. So that tells me that either something's come unsoldered or we finally had a component failure. At the end of the day, the result to me verifies the same thing, and I feel very comfortable about my statements I've made about this supply. This is by far safer than anything else that we've come up with yet in the radio industry. I'm sure there's something else out there that I've yet to discover or somebody else hasn't already brought to the game yet. So let's go over the numbers here. Let's slide this forward so I have a little bit more room for the graphics. It's up here someplace. I'll put in something. Okay, so before we modded the supply, the most that we could get out of it on 220 was 80 amps at 12 volts. Anything over that, and we would see it drop dramatically below 12 volts. So it's the control board. The most that we could get out of it before the crowbar would pull it and shut it down was 127 amps at 10.2 volts. Once we modded the supply, we were able to pull 132.9 volts at 12.24, or pardon me, 132.9 amps at 12.24 volts, which is a huge increase in current capability, but it's the major increase is in the voltage. All right. Now the max amps is of course 133.2 amps, and that's at 8, and this is where the crowbar protection kicked in, was 8.29 volts. So the results stand as it is. We've shown that we can put over 100 amps on it for over 30 minutes without having any component failure, without the power supply having any failure whatsoever. Period. So then we decided we would move into the set of testing where we were going to be negligent and abusive to the supply, where we left the lid off and we didn't let anything get any airflow on it, and we overclocked it and we held it at the most destructive amp level that we could possibly get it to go to, and the only thing that happened was the supply shut off. If we would have had the lid closed, the supply probably would have brought itself back from being in the dead mode that it currently sits in. I don't care, I'll kill one of these just to prove a point. The point is if you deviate away from these numbers, the supply is smart and it is constructed with so much safety integrated into it that when it fails, one, it can't or will not damage your components in any of your other equipment that's attached to it, which is the biggest freaking plus on the face of the earth, in my opinion. With those 30 amp switchers that we were using before this, that shit would fail and parts would come flying out of it and smoke would come flying out and there'd be flames, and then all your equipment you had attached to it could have been damaged. I mean, it could have had 330 volts AC dropped on it. I mean, there's a lot of shit that went on with those 30 amp modules, causing a lot of damage. We're not seeing the failure with these be the same. This is by far, hands down, way safer than anything else to use as a power supply module on the market right now. The results are in the test. Now, as far as people dragging themselves up on the cross and saying, well, I feel the builders need to quit doing this, that, and the other thing, or otherwise it's going to be dangerous. Dangerous how? I mean, dangerous how? We just took it and tested it as hard as we could, right? We got it way hotter than it would ever let itself go. We bypassed all the main things that we have our ability to put our fingers on and twist knobs on. And at the end of the day, the worst that happened is the power supply just shut off and won't turn back on. There was no flames, there was no huge voltage spike, there was no ambient trace voltage that floated out through the atmosphere and caused children to have third eyes growing out of their buttholes. None of that happened. So let's stop with the melodramatics, y'all. And believe me when I tell you, I tested all of this already once. I just didn't do it on video for you guys to watch. So the next person I see make a comment like that, I'm going to be like, okay, where's your data? Prove it. Because here's my data. I backed it up. I mean, we beat on this supply. We got it hotter than hell, then we bypassed all the safety circuits and then still went on to run for another 15 minutes, being run at 150%, 180% of its output, almost into a dead short. And we still had no major failure in the supply other than it shut itself off. And when the supply died, the end result was it just shut off. So unless somebody's being absolutely flagrantly abusive to the supply, in my opinion, this is the safest thing that we possibly have to run. And even our little modifications to turn in the voltage up and down, and coming away from the data sheet on this thing just a little bit by a couple volts, I don't see it opening up the door to where somebody else is going to have some kind of major failure, or they're going to end up having some kind of problem in their station as a direct result of this supply failing. I'd have a hard time believing it. Now, we're talking, these are C-beers now, right? Let's face it, a little bit harder on shit. They might find a way to where there's a problem, but that's going to be a very small, isolated case. So I cannot get behind this, just like a scientist will never get behind anything and say, oh, that's completely impossible. 99.99999% of the time, there's not going to be any issue, but there's always that 0.0000001% chance that somebody out there is going to create a situation with how they've modded the supply to where it might cause them specifically a singular issue. But for the majority of us, I don't feel that this is a huge risk. I feel like this is the safest thing that I could have brought to the table. And I stand behind my original statement stating that this is better than anything else that we've got elsewhere. This is my opinion. Gentlemen, shout out to Penna. Remember, mention BBI at checkout, you get 5% off the purchase and shipping and whatnot. Excess Power, thanks to them guys, Siglent and McMahon, Bird, Coaxial Dynamics. And always, if you got any questions or comments, not about this or about anything else, including this, I guess, give me a call. Let me know what I can do to help you out. Gentlemen, my name is BBI, and without a shadow of a doubt, I'm the biggest mud duck in Idaho. I appreciate every single one of you guys. I got to run. I got other stuff I got to go work on. I'll see ya. Click, click.